We've investigated how to discover the electric field from a volume of charge. But so far we've only considered uniform volumes of charge. Now let's look at a non-uniform volume of charge. So we have a sphere, non-conducting, radius r, and inside this sphere we're going to check out what the electric field is. The particular volume charge density I'm going to use is delta r to the fourth. So that's a very strong relationship to the radius. So I'm just kind of picking that out of the sky to see how we handle this. Well, the hint here is we're going to take an infinite number of thin shells to solve our problem. So the total charge, first of all, of this shell is going to be important to find, because it's going to be a function of r, but we will find out actually what the total charge of this sphere is. So it's the integral of all the dq's until we get to q. So q is the total charge, and it's adding up all the dq's. And the dq's has to be specified. Well, a dq, differential charge, of a thin shell is the volume charge density times the differential volume. Well, what's the differential volume of a thin shell? The differential volume is the surface area of the shell, which is 4 pi r squared, times its thickness dr. And so these are the thin-shelled volume elements. So here's what it looks like. We stack those thin shells on top of each other, and there's an unlimited number of them, each one having its own increasingly large volume charge density that makes up that particular shell. So that's the proper way to handle getting the total charge of the sphere. So rho delta r to the fourth comes inside the radicand, 4 pi r squared dr, from 0 to r. Well, that's the integral we have to solve. The 4 pi comes out as well. R fourth and r squared gives us r to the sixth dr. So when we do that integral, we get r to the seventh over 7 from 0 to r. 4/7 pi delta r to the seventh is the answer to the question, how much charge does this sphere have in total? And there it is. Now let's solve for the electric field as a function of r. Well, most importantly, we want to discover the electric field inside the spherical non-conducting object of non-uniform charge density. And so we have our radius being less than cap r. And we put a Gaussian surface in there and write Gauss's law. The flux is equal to the closed integral of E dot dA, which is Q enclosed over epsilon 0. Because of this unique nature of our Gaussian surface, E is constant, and it's dotted with dA, and the vector dA direction is everywhere in the same direction as E, so it's just all EA. Very wonderful. And in summary form then for E, we have the simplified algebra that should just be rolling off your tongue, which is that E is equal to Q enclosed over epsilon 0A. There it is. And now, let's assume, even though we just solved for Q enclosed on the previous slide, let's assume we're starting from scratch, and I'll do it again for you. So you're integrating from 0 to r of all the rho dV's. And the dV's are the spherical shells. So that's some physics knowledge that you're imposing upon this. And the rho is as given. So this is rho 4 pi r squared dr. And it's over 4 pi r squared, or the area. And the area of the shell is 4 pi r squared. Now the constants will divide out here. We can't just divide out these r squares because we're integrating this r squared. And so once we get done with this operation, then we can do any cancellation with r. So the integral of rho is delta r to the fourth times r squared dr over epsilon 0 r squared. And carrying that, simplifying, bringing together, we have r to the sixth in the radicand over epsilon 0 r squared. Integral of r to the sixth becomes r to the seventh over 7. So there's the 7. And now we can eliminate two of those r's. and we have delta over 7 epsilon 0 r to the 5th from 0 to r, which gives us our result that the electric field inside the non-uniformly charged conducting sphere is delta r to the 5th over 7 epsilon 0. And now let's find it in the rest of space. Well, you should be getting used to the fact that when we look for the electric field outside of the object, it gets easier because we're enclosing all the charge. So here's our Gaussian surface, enclosing all the 4/7 pi delta r to the 4th charge, r to the 7th charge, sorry. So flux equals closed integral of E dot dA, Q enclosed over epsilon 0, which is EA. So E is Q enclosed over epsilon 0 A. Q enclosed, there it is, area 4 pi r squared. The electric field then is delta r to the 7 over 7 epsilon 0 r squared. And the only thing left to do is just to make sure we know the E field at r equals big R. Well, we have the same formula, but instead of little r here, right here, we have big R squared because that's where we are. So E is delta r to the 5th over 7 epsilon 0. And now we know the electric field in all of space.